Hello, my name is Dennis Morris. I'm a mathematician and a theoretical physicist. In this video, I'm going to derive the Quaternion form of the Dirac equation. Before watching this video, you are advised to watch the video entitled The Dirac Equation, produced by myself and also available on YouTube. This video also presumes that you are familiar with the left chiral quaternions and with the right chiral quaternions. We also presume that you are familiar with non-commutative differentiation. If these concepts are unfamiliar to you, you are advised to watch the two videos on quaternions produced by myself and also available on YouTube before you watch this video. We will begin as Dirac began. We will begin with the relativistic energy-momentum relation. This is the relativistic energy-momentum relation. Notice that the right-hand side is of the form of the norm of the quaternions. We will continue as Dirac continued. We will seek a root of the right-hand side of the relativistic energy-momentum relation. However, at this point, we diverge from the path followed by Dirac. We notice that the right-hand side of the relativistic energy-momentum relation has a quaternion root. We will go down that path. Here we have used a left chiral quaternion. This is the left chiral quaternion root. It turns out that this is the matter left chiral root. There is a second left chiral quaternion root of the right-hand side of the relativistic energy-momentum relation. Since the relativistic energy-momentum relation is a quadratic relation, we might have expected this. Here we have the other left chiral quaternion root. This is the antimatter left chiral quaternion root. We also have two right chiral quaternion roots. This is the matter right chiral quaternion root. This is the antimatter right chiral quaternion root. We have not had to play around with 16-dimensional Clifford algebras as Dirac did. We have gone straight to the roots of the matter. It will turn out that the left chiral quaternion root corresponds to the left-handed electron of electroweak theory. The right chiral quaternion root corresponds to the right-handed electron of electroweak theory. The other two roots correspond to the left-handed positron and the right-handed positron. You will recall the gamma matrices that we met in the previous video. These are the relations of the gamma matrices we met earlier. The quaternion variables have exactly the same relations except that the gamma 0 of a quaternion, the real variable, commutes with all other variables. We can put any of these roots into the relativistic energy-momentum relation. Here we have used the matter left chiral quaternion root. We have the energy is a real number, as is the mass. At zero velocity, the momentum is zero. The viewer might wonder why we have chosen the conjugate root. We have chosen this root to fit with the arbitrarily defined direction of the electric and magnetic fields which will fall out of this mathematics. This is just a small notational change. We have moved the momenta to the left-hand side of the equation. So what do we do next? We substitute into the root the quantum mechanical operators for energy and momentum. This is exactly what we did when we derived the 4 equations of particle physics in the previous video called the Dirac equation. We are following Dirac's procedure. We have taken the i's to be the imaginary parts of the quaternion. These are encoded in the distribution of the matrix variables, and so we do not need them. We have ignored the I on the energy operator, which we feel is a result of writing the operator in a particular basis. We have set Planck's constant to unity, as is normal. We have the left chiral quaternion differential operator. An operator needs a field to act upon. We saw in the previous video how both Schrödinger and Dirac inserted a field into the equation. We will do the same. We will insert a field into the relativistic energy-momentum relation root. Schrödinger inserted a single complex number as his field. Dirac inserted a Dirac bispiner, an ordered pair of ordered pairs of complex number, into his equation. We will insert a left chiral quaternion into the relativistic energy-momentum relation root as our field. Our field is going to be a left chiral quaternion field. To be mathematically consistent, since we are working within the left chiral quaternions, we need to insert only, this is the only thing we can do, insert a left chiral quaternion as the field. That's all we can do. Let me remind you that under the inner product operation within particle physics, a quaternion can be written as an ordered pair of complex numbers. So if you like, you could take the view that we are inserting a Pauli spiner into our energy-momentum relation. We will insert this left chiral quaternion potential into the equation as the field. So what does the root of the energy-momentum relation now look like? This is the left chiral quaternion root of the relativistic energy-momentum relation. Okay, we know where we're going. We're going down the same path that Schrödinger, Pauli, Dirac followed. At this point, Schrödinger and Dirac inserted into their equations the energy and momentum operators of quantum mechanics. These are commutative operators from the commutative complex numbers. We will not do that. We will insert into our equation non-commutative differential operators. We must differentiate within the quaternions non-commutatively. And so we will use non-commutative differential operators. The details of non-commutative differentiation within the quaternions are presented in the previous two videos upon quaternions available on YouTube, produced and presented by myself. Non-commutative differentiation will give us the E field and the B field. The left derivative, d subscript L, is formed by letting the differential operator act as if by matrix multiplication on the potential from the left. The right derivative, d subscript R, is formed by letting the differential operator act as if by matrix multiplication on the potential from the right. Doing the calculation leads to the quaternion form of the equation for the electron. The matrices are too large to show easily upon the screen, and so we will show only the top row elements of the matrices. Since each matrix is a left chiral quaternion, we can simply copy these elements into the different positions in the matrix, provided we watch the signs, and we have the whole matrix. Putting the E field equal to the right-hand side of the root of the relativistic energy-momentum relation gives this. Viewers familiar with electromagnetism will recognize that we have here an electric field. Phi is the potential in the time direction. At any instant this will be zero, and so we have a zero divergence which we associate with a conserved charge of some kind. Within our space-time, m, which is just a real number, is taken to be mass, but within quaternion space it seems that the m corresponds to electric charge. However, it seems that m also means mass when an observer in our space-time observes the quaternion field. It seems that m has two meanings. In quaternion space it means electric charge, in our space-time it means mass. Thus, this field has both electric charge and mass. This is a left chiral quaternion matrix. We opine that this is the left-handed electron field. We are taking the left-handed electron to be a left chiral quaternion field. I'll repeat that. We are taking the left-handed electron to be a left chiral quaternion field. Non-commutative differentiation also gives a B field. Putting the B field equal to the right-hand side of the root of the relativistic energy-momentum relation gives this. Viewers familiar with electromagnetism will recognize that we have a magnetic field here. If M corresponds to electric charge in quaternion space and to mass in our space-time, then this field has no electric charge and no mass. This is a left chiral quaternion matrix. We opine that this is the left-handed neutrino field. Since the M is 0, the field is 0. We would not expect such a field to interact with anything. Dirac arrived at the electron field. Physicists took the neutrino field to be the electron field with zero mass. Since the electron field is non-chiral and the neutrino field is chiral, neutrinos are left-handed, this idea holds no water. We have come to two separate fields by using non-commutative differentiation. One will be the electron field, the other will be the neutrino field. Well, what we can do with the left chiral quaternions, we can do with the right chiral quaternions. First, the E field. The top row of the right chiral quaternion E field is identical to the left chiral quaternion E field. However, the two matrices are different, and it is the full matrix which is the field. The chirality of the quaternions is encoded within the bottom right-hand 3x3 corner of the quaternion matrices. We see that the signs in the bottom right-hand 3x3 corner of the quaternion matrices are the reverse of each other. And the B field? The top row of the right chiral quaternion B field is the reverse of the top row of the left chiral quaternion B field. It is the reverse. Of course, it is the full matrix which is the field. It seems that we have a left chiral electron field. We also have a right chiral electron field. We also have a left chiral neutrino field. And we have a right chiral neutrino field. This is very reminiscent of electroweak theory. Well, what are we to do with these right chiral fields and these left chiral fields? We will take our lead from electroweak theory. We will form superpositions of these fields. We will add the left chiral electron field to the right chiral electron field, and we will add the left chiral neutrino field to the right chiral neutrino field. We call that taking the superposition of the fields. We form the superposition of the left chiral quaternion E field and the right chiral quaternion E field by simply adding the field. The factor of 1/2 is just a convenience. Because the signs of the two fields are opposite in the bottom right hand 3x3 corner of the matrix, the superposition matrix has zeros in these positions. This means that this field has no chirality. This is neither a left-handed field nor a right-handed field. This is an electric field. We think this is the field of the electron as we observe it in our four-dimensional space-time. We put the electron field into the root of the relativistic energy-momentum equation. We have similarly taken the superposition of the two mass matrices on the right-hand side of the equation. This is the Quaternion Dirac equation of the electron. And now the B field. Because the signs of the right chiral quaternion B field are the reverse of the signs of the left chiral quaternion B field, the elements on the top row and in the leftmost column of the superposition matrix are all 0. However, because the signs in the bottom right-hand 3x3 corner of the quaternion matrices are the reverse of each other, these elements are non-zero. The chirality of the quaternions is in the bottom right-hand 3x3 corner of the matrices. This superposition matrix is a chiral field. Furthermore, looking at the distribution of the minus signs, this superposition is a left chiral field. We think this is the field of the neutrino as we observe it in our four-dimensional space-time. This fits with observation exactly. We know that all neutrino fields are left-handed. The antineutrinos are right-handed. This fits observation. We put the neutrino field into the root of the relativistic energy-momentum equation. We have similarly taken the superposition of the two mass matrices on the right-hand side of the equation. This is the Quaternion Dirac equation of the neutrino. Since the m is 0, this field is 0. We would not expect such a field to interact with anything. We have seen that the neutrino field is a zero field within our space-time. Neutrinos do not interact very strongly, but they do interact sometimes. What's happening here? It seems that neutrinos interact in quaternion space. In quaternion space, the neutrino field is non-zero. The relativistic energy-momentum relation is a relation within our space-time. The neutrino field is zero in our space-time, but the neutrino field is not zero within Quaternion space. Only when we try to fit a neutrino into our space-time does the neutrino field become a zero field. Let us think a moment. Both mass and electric charge are real numbers. How do we get a real number from the non-zero neutrino fields in Quaternion space? We take the inner product. The inner product exists within all division algebras, and so Quaternion space has an inner product, and that inner product is a real number. Whether we take the neutrino field of the left chiral quaternions or of the right chiral quaternions, we get the same inner product. A superposition of these two inner products is just the inner product. We have a real number, the inner product, associated with the neutrino field. Within our space-time, we associate mass with a real number. We have a real number from the neutrino fields. It seems that in our space-time, neutrinos have mass. Well, it's squared mass. It is the neutrino field squared that has mass. It is well established experimentally that neutrinos travel at the speed of light. This implies that neutrinos are massless. It is well established experimentally that neutrinos oscillate between generations. This is the probability of an electron neutrino becoming a muon neutrino. We see that this probability will be zero unless the two types of neutrinos have different squared masses. This is often taken to mean that neutrinos have mass, but that is not strictly necessarily correct. It seems that neutrinos are massless, but that they have a squared mass associated with them through the inner product. This allows neutrinos to change generation as they travel through space. One of the great triumphs of the Dirac equation was that it predicted the positron. Can we do that? Yes, we can. There are four roots of the relativistic energy-momentum relation. Four Quaternion roots, that is. So far, we have considered only two of them. Here we have the other left chiral quaternion root. We call this the antimatter quaternion left chiral root. We see that the signs of every element of the quaternion are reversed. In particular, the sign of the real part is reversed. Within Quaternion space, we associate the real part of the quaternion with electric charge. If we calculate the E field of these antiquaternion roots, we get a reversed electric field. The same is true of both the left chiral and right chiral antiquaternion roots. We have the positron. What about the B fields of these antiquaternion roots? If we calculate the B fields, we get a right chiral neutrino field. We get this from both the right chiral quaternion, antiquaternion, and the left chiral antiquaternion. We have the antineutrino, and it is right-handed. It is within the nature of quaternions that the real part can be either negative or positive. This is what allows the positron, the anti-electron, to exist. But there is a great imbalance within our universe between matter and antimatter. Why should there be such an imbalance? We do not know. This is something we do not understand. In a video we hope to produce shortly, we will show that the reflective symmetries of quaternion space are charge conjugation and CP invariance. CP invariance is never violated within the lepton sector, that is the electron and the neutrino, of the standard model. Of course it isn't. You can't violate the symmetries of a space. Now a summary. Using non-commutative differentiation within the quaternions, we got two fields for each of the four quaternion roots of the relativistic energy-momentum relation. We took one of these fields to be an electron field. We took the other of these fields to be a neutrino field. We thus had a left chiral electron field, a right chiral electron field, a left chiral neutrino field, a right chiral neutrino field within the matter roots. We took the superposition of the two electron fields by adding them together. This produced the actual electron field. We took the superposition of the two neutrino fields by adding them together. This produced a left chiral neutrino field with zero mass. We did the same with the two antiquaternion roots. This produced a positron field, the superposition of the left chiral positron and the right chiral positron field, and it produced a right chiral neutrino as the superposition of the left chiral anti-quaternion neutrino field and the left chiral anti-quaternion neutrino field. We have now come to the end of this video. Please allow me to advertise some of the books I have written. Thank you for your attention.